Afternoon to all. I request all please mute yourself. A very good afternoon to all. Now for the third session of our first day, I want to introduce our eminent speaker, Dr. Mukesh Bhesaniya sir. Dr. Mukesh Bhesaniya sir received the Bachelor Engineering degree in Electrical Engineering from the Sardar Patel University, Gujarat in 2000. He had completed a Master M.Tech in Electrical Engineering from IIT Kanpur in 2009. The PhD degree in Electrical Engineering from IIT Bombay in 2017. He has received Academic Excellence Award for the best academic performance during Master in Electrical Engineering from IIT Kanpur. In 2003, he joined a G.H. Patel Engineering College, where he is currently as an associate professor in Department of Electrical Engineering. He has published and present number of research papers at national as well as the international journal as well as the conference, and he has been granted a US patent for invention in power electronic converter. He has also filed one national patent for invention in power electronic converters. He is a reviewer of IEEE transaction on power delivery in I3 as well as IEEE transaction on industrial application. His research interests include power electronic converter, HVDC, and flexible AC transmission system. So I request Mukesh Bhesaniya sir to just deliver his expert talk.
Yeah, hello. Am I
Yes.
audible, Dhaval?
Yes,
Yeah.
sir. You are audible,
Yeah,
sir.
thank you very much for the introduction. And good afternoon to all. Now, let me first share my presentation. Yeah, so is my PPT visible?
Still not, sir.
Just
Yes,
a second.
yes. Now, yes, sir. Now it's visible.
Okay. Okay, so again, good afternoon to all. And this is a after lunch session, and you already attended two sessions of this FDP. So I understand that it is difficult to continue with the third session. But anyway, I will try to keep as interactive as possible. Now, the topic of our discussion in this third session is on converters, specifically for the electric vehicle applications and its control, right? And as I got the feedback from the organizer of the FDP that the participants in this FDP are from various backgrounds. They are not all from the electrical background, and also all the faculty may not be working in the field of the power electronics converter. So my objective in this session is not to give in-depth knowledge of any types of a converter, or will not go into a much detailed mathematical analysis of a converter, but just to give the overview of a type of the electric drives, motor drives, which are used in these EV technologies, and what are the types of converters which are used for these electric vehicle applications. Okay, so let us start. So the first these are the content of my presentation, and I will briefly explain about motor drive technology. Then I will talk about DC drives, the configurations of different DC-DC converters which are used for the DC motor control, brief overview of isolated DC-DC converters, which are also apart from the main converter for the electric motor, DC motor. They are also used for this auxiliary power supply in EV. Okay, and many these EV manufacturers have also they are using, like say in a Ford vehicle, you will also find such type of isolated DC-DC converter, which are used as auxiliary power supply. Then another thing, when you use this DC-DC converter is a soft switching. Okay, so in literature you will also find there is a soft switching technology which is used, or the concept which is used for a DC-DC converter to improve the reliability, efficiency of a converter. We'll briefly talk about the induction motor drives and related converters, and how these inverters are being controlled in an induction motor drive, and then we'll discuss about permanent magnet synchronous motor and permanent magnet these DC motor, BLDC motors. Okay, I'll give you the brief overview of the types of drives which are used and the converter configurations which are used in EV application. Right. So just before we go into the detail, the brief history of the EV. Okay. So now, as you all know that these EVs are not new, right? And if we go into the history, then you see that they were invented 185 years ago. Okay, but they lost the competition for the dominance to the IC engines, which are presently widely used in all the vehicles. Okay, so the first this EV, if you go into the history, then was a battery powered tricycle which was built by Thomas Davenport in 1834. Okay, it was around 185 years ago. Okay, and if you see in the United States, I have taken this data from a paper. If you see in 1900, among an annual sale of around 42 vehicles in US, 38% were EV. So the contribution of EV, you can see they were around 38%, then 22%, which is lesser than that of EV, and 40% were steam powered vehicles. Okay, so at that times EVs were the preferred road transportation among the wealthy elite, and the cost of these EVs were equivalent to the Rolls-Royce of today. Okay, but then after the man who spoiled this market of EV was the Ford. Okay, so the man with an idea that finished off the EVs for the good was the Ford. Okay, so his mass produced Ford Model T could offer a range which was double or a triple than the EVs, but at only a fraction of their cost. Okay, and subsequently by 1930s, these electric vehicles almost vanished from the scene. Okay, and then after, the rebirth of interest in the EV started at the outbreak of energy crisis and oil shortages in 1970s. Okay, then the people slowly started about talking about these electrical vehicles, and the main concern was the pollution at that time. Okay, and presently, if you see, apart from the pollution, no doubt all the federal governments across the world are having an ambitious the target for this EV in the coming days or coming years. Okay, but now from the customer point of view, as you can see, the fuel prices are also increasing day by day now, right? So that is also one of the concerns as a customer. Pollution is no doubt the main concern for the governments, and this energy crisis is also this another concern that we have. Okay, so due to this growing concern of this air quality and possible consequences of these greenhouse effects, in the 1980s, again the pace of EV development was accelerated. Okay, and you see, a few days back, this Ola started the booking of that scooter, right? And within a 24 hours, more than 1 lakh people booked that two-wheel scooter, right? So you can see the people are also interested in going for this electric vehicle. Okay, no doubt there are many challenges, and that's why we are talking about this electric vehicle nowadays. Okay, so Presently, as you know that this pure electric vehicle or PE we call it, they rely only on the battery. Okay, so the batteries are their sole or a major energy storage. To store the electric energy. You can also have some these ultra capacitors, but the capacity of that energy storage is very less compared to that of a battery. Okay, and therefore these EVs is sometimes also named as a battery electric vehicle. Okay, so instead of just telling about this in a literature, you will also find this abbreviation BEV, that is battery electric vehicle. Okay, and at the present status, you see of the battery technology, the energy storage, this capacity of EV is far less than that of these IC engines. Okay, so typically, if you talk about a simple passenger car, under the urban driving with air conditioning, say, the PV can travel about around say 120 kilometer per charge. Okay, so that's maybe more than that. Okay, so around say 150 or so. Whereas if we talk about the conventional this vehicle, then they can offer more than 500 kilometer for refuel, right? So with such a short driving range for per charge, these EVs will suffer from the problem of the range anxiety. Okay, so obviously if you have to go for a long travel or a long distance travel, then you will not utilize these EVs, right? And there are other challenges as well, right? Specifically in the battery technology. Okay, so we'll not go into those challenges related to battery technology right now, but you will find a lot of work which is going on. Specifically, say there are two aspects. One is you have an electric motor drive, wherein you have an electric motor. So electric motor is one area where the people are working, and then you have to transfer the power from battery to this motor. Okay, so in between you have an interface which we call it as a converter. Okay, so again, based on the type of motor that you are using, based on the type of control that is being expected from the motor, you have a different configurations of a converter, different types of control methods which are being used. Okay, and it's not very straightforward. Okay, so if you go into the detailed control aspect of these EV motors, then it's very complicated. Okay, so you have to see many things you have to consider while designing the controller for these EVs. Okay, and another area is you must be aware about is the charging technology. Okay, so you must have the fast charging technology. Now the people are also talking about the concept of a battery swapping. Right. So that is also one of the business model which is being reported in the literature, wherein what can be done is you swap the battery instead of going for the battery charging. There are certain swapping stations. No doubt the size may be much larger, and where you just swap your discharge battery with the charge battery. But there are many other aspects related to the business associated with those type of a model. Okay, but that is also reported in the literature to just to think of out of box regarding this charging of batteries. Okay, so now if we talk about right now, our discussion is related to this the motors and related converters. Okay, so if we talk about this motor drive technology, then again you will find a lot of motors which are used in the EV. Okay, so mainly these DC motors are used. So the one technology which is used is a DC motor drive, and because see basically these motors are being powered through a battery, right? And the battery is having a DC voltage, so you just have an interface of that DC-DC converter in between this battery and the motor. You can regulate the voltage with the use of that DC-DC converter, right? So the one technology that is used is DC motor. Again, in that DC motor, you have the commutator motors, that is also known as the brushed DC motor and the brushless DC motor. Okay, so I'll briefly talk in the last topic of this discussion. Then another is AC motors. So generally for high power, these EVs, these induction motor drives are preferred, and we'll also discuss about those inductor drive motor. Then people also talk about this the permanent magnet brushless motors, wherein you have that permanent magnet synchronous motor, which we call it as a PMSE motor, and another is a permanent magnet brushless DC motor. Okay, there are other configurations also people are working on. One is this switch reluctance motor. Then you also find in a literature related to this stator motor, stator permanent magnet motor drive. Okay, stator where the stator is a permanent magnet. Okay, there are also these machines related to this what I call it, I forgot that magnetic geared motor drive. Okay, so people, you will also find some papers on a magnetic geared motor drive. Then Vernier permanent magnet motor drive. So a lot of motor configurations are being studied by many people, and still you do not find the matured the motor drive technology for the this one the EV. Okay, so people are still working on a different configurations based on that performance. Okay, so when the full-fledged EVs are used by the people, then only you will come up with the matured motor drive technology. Okay, now whenever you are talking about any type of a motor which is being used, hello, am I audible? Okay.
Sir, yes.
Yes.
Yes, sir.
Okay. So some disturbances were there, so I thought, yeah. Okay, so when you talk about this type of machines which are used for this EV, or specifically we call it as a pure EV, then there are certain requirements. Okay, and these are some of the requirements. Okay, I'll quickly go through this. So one of the requirement is this the high torque density and the high power density. Okay, wide speed range covering low speed creeping and high speed cruising, right? High efficiency over a wide torque and speed ranges. Okay, so you need to just check out these torque speed characteristic, and based on the operating the region in that torque speed characteristic, you should work out on the efficiency aspect of the machine. Then wide constant power operating capability, high torque capability for electric launch and hill climbing. These are some of the requirements specifically for the vehicle. Okay, it depends on the environment under which you are operating your, or you are using these EVs. Then high intermittent overload capability for overtaking. This is also one of the important the aspect which needs to be considered while selecting these electric machines for the EV. High reliability and robustness for the vehicular environment. This also will be one of the important criteria or the requirement for the machine. Low acoustic noise, and obviously the reasonable cost. Okay, you can achieve all these characteristic, but if the cost is very high, then you need to look into the optimal the design of any of the machine. Okay. Now if you see the configuration in general, this is a simple the block diagram representation of the EV, right? So here you can see mainly from the electrical point of view, if we talk, then we'll be focusing right now on this two part. Okay, so you have an electric motor. Okay, based on the type of EV that you are using, you have either a DC motor, or you have an induction motor, or this permanent magnet brushless motor, or even a switch reluctance motor. Okay, so different types of motors are used by the different manufacturer of electric vehicle, and this is a power converter, and the design and the control of this power converter is very important, right? And this is feeding power to the motor through a battery. So here you have an energy storage element which is nothing but a battery in a pure electric vehicle, and this is the energy source, and it will supply energy to the electric power converter. So this may be a fixed DC voltage, and you will get a variable DC voltage with the use of different types of a converter. Okay, say if you have this DC motor, then we use a DC-DC converter, wherein the input is a fixed DC voltage, output will be the variable DC voltage. If you are using this induction motor drive, then in induction motor drive, the drive is fed from this inverter, three-phase inverter. Okay, and the function of that inverter, in general we call it as a power electronics converter. Okay, for all these machine, those are the power electronics converter which convert the power from one level to the another level. Okay, so you are just transferring the power with a different parameters. Right, so the different parameter means, in case of say inverter, the input to the inverter is a DC voltage, and that you either directly get it from the battery or in between. Generally, like say if we one of the vehicle, just a few days back I was just referring one paper, I think it was from Nissan. Okay, so they are using this AC motor, and in that induction motor they are using inverters. Those inverters are not directly fed from the battery, but those inverters are fed from the DC-DC converter. So you will have a regulated this DC supply on the input side of a converter, and then after, sorry, on the output side you will have a variable DC supply, or you can keep it constant by properly controlling the duty cycle of the inverter, right? Sorry, the converter. And then depending upon the type of control strategy that you use in the inverter, like say the inverters can be operated in a 6-step mode, or you can go for a pulse width modulation. Okay, people are also using this space vector modulation. You will find a lot of paper in which paper specifically, see, we are talking about the EV. Okay, so whatever reference or whatever paper, I'm saying that paper related to these EVs only. Okay, so in that for the industrial drive, this space vector modulation is very common method which is used for the control of an inverter. Okay, and in many these drive applications, this space vector modulation is used. So here in the EV also, that space vector modulation is used. Okay, so ultimately you have to control this converter. Okay, so based on the vehicle that control signal that you get, you will have this controller which controls the power electronic converter based on the required speed or other parameters. Okay, so other things will remain same. Okay, so you have an accelerator, you have a brake, you have the steering wheel. With the use of you just move the wheels and all this, right? And this is a mechanical transmission. Again, in many configurations you will find two motors which are installed on both the wheels. Okay, or you have a single motor with the use of this mechanical transmission. Okay, it's a differential type of mechanism which is used. Okay, specifically say when you are going for a cornering action, then in a cornering action the two wheels may not be rotating at the same speed. Okay, so that has to be, so they will not spin at the same rate. So you need to adjust it with the use of these differentials, which we call it as a mechanical transmission here, right? So this is a basic configuration of a EV, and we'll be talking about this the drives, which consist of a motor and this converter. So if we, I already mentioned some of these the machines which are used in this EV, right? So here you see mainly or broadly these machines can be classified into two categories. One we call it as a commutator based machine. Okay, where you have brushes. Obviously the maintenance of this type of these machines will be higher because of the brushes which are used, or the commutator which are used in the machine. Another is a commutatorless, and nowadays these machines are more widely preferred compared to that of a commutator motor. Okay, so if we talk about the basic commutator motor, we have a DC motor wherein you can have a wound field or a permanent magnet field. Okay, and again this wound field, these machines are again, hello, will you please turn off your mic? Okay. You will find different configurations of these machines. Okay, like based on the connections of the field winding with the armature. The field may be connected in series with the armature. It may be connected in parallel with the armature, or the field and armature are separate. Okay, they are not directly connected. Okay, so they are known as a separately excited DC motor, and in some of the EVs presently these separately excited or shunt motors are still used. Okay. Another group is a commutator-less motor, wherein the main motor is this induction motor, and here also these cage rotor induction motors are widely used. Okay. If you talk about the synchronous machine, you have these two configurations which are reported in the literature, where the people find the attention for the EV, that is a permanent magnet brushless AC motor and permanent magnet brushless DC motor. This is nothing but a permanent magnet synchronous machine. Okay. You also find some this literature or some applications of switch reluctance motors which are used in these EV applications. Okay. There are other configurations which are used, but not discussed in the literature, but not used practically for the EV application. Okay, some of the configurations are already used in practical EV applications. Right. So let us start with this DC motor drive. Now this DC motor, if we talk, then these are widely used for this EV propulsion, and as I already mentioned, various DC motor drives were already applied to different EV, and the main the advantage, if you see, then it's a matured technology and simplicity in the control. Okay, so the control is very simple compared to that of an induction. So those who are familiar with the control aspect of these inverters, okay, in an induction motor, they must be knowing about how complex it is to implement the control of the inverters for the induction motor drive in comparison with that of the DC motor. Okay. They are matured and control simplicity. However, as I already mentioned, they suffer from the problems such as the lower efficiency and the lower power density than their AC counterparts, and the one of the main problem is the need for a regular maintenance because of the carbon brushes and the commutator. Okay, so consequently, besides those small or off-road EVs, they are superseded by the AC or a brushless DC motor drive for EV propulsions. Okay, now this is a basic configurations that is already shown in a previous slide. Okay, so you can see here you have an electric motor drive, and this is a energy storage device that you have. It's a battery. Okay, and this will supply is to the mechanical transmission. Okay, so it's a single motor EV drive that we have. Now if you see the basic configuration, then this is the energy storage you have in a DC motor drive, and this is your DC machine. Okay, based on the speed requirement, the gears may be connected with the mechanical transmission, or this may be directly connected with a low speed this one. Okay, the drive applications, right? So this DC motor is fed from the DC-DC converter. So you have a controller, you have some sensors. So mainly you sense the speed and the current. Okay, the speed generally you have a reference for the operation of a DC motor. Current feedback is generally used for the protection purpose. Okay, so because it should not exceed the rated current of a motor. Okay, so the output of the sensors is provided to the controller, and you have a command from the accelerator or from the brake or some other these inputs, and then controller will generate the reference signal for the converter. And when you have a DC-DC converter, the output of the converter is varied. So here on this side, on the input side, you have a fixed DC voltage, and on the output side you have a variable DC voltage, and by varying the DC input voltage to the machine, you can vary the speed of a DC machine. Okay, so mainly, see, there are two main control. I'll discuss in a subsequent slide. One is, we call it as the armature voltage control, another is a field weakening control. Okay, so by changing the armature voltage, or by changing, so in case of this what would say separately excited DC motor, the field voltage is generally constant. We keep it constant, and then we vary the armature voltage with the use of this DC-DC converter. Okay. You can have another converter which is connected with a field for the field weakening control. Okay, but they are controlled independently. Okay, so here the input signal to the DC-DC converter will be the duty cycle. So that I will explain here, and based on the duty cycle which is being generated by the controller, you will have the required voltage, input voltage to the machine, and your machine will run at the desired speed. Okay. So if we talk about the speed control in a separately excited DC motor, so this is your DC machine. It's armature controlled. This is armature control, and this is a field control. Okay, so this is a configuration of a separately excited DC motor. So the armature may be, so this is your battery, or this may be the energy source that you have, and this is connected to the input of both this DC-DC converter. One DC-DC converter or the chopper is feeding to the armature of a machine. Another DC-DC converter is feeding to the field winding of a machine, right? And the speed, if you see the, okay, I'll have those some of the expressions at a later stage I will show you. Then by changing this armature voltage or the field flux, you can have a different speed torque characteristic, right? So speed can be varied by either changing the armature voltage or by changing the field voltage. But is this armature voltage can be controlled up to its rated voltage. So generally what is done in the control is you control the speed of a motor by changing the armature voltage up to the rated speed or up to the base speed. Beyond the base speed, if you want to control the motor, then you need to change the flux, you need to reduce the flux. Okay, because the speed is inversely proportional to the field flux, and by changing that field voltage, you can then increase the speed further by keeping the armature voltage constant, right? So as I mentioned, in general, the speed control of this machine can be accomplished by these two methods. The first is armature. Hello.
Can I ask a small question? Why do we weaken the field weaken the field? Why not strengthen the field of the field magnet, field or winding? Yeah. Why do we weaken it?
Yeah, yeah. See, if you yeah. So this is what we have. If you talk, I'll explain in this characteristic. Yeah, I got your question. See, we have two types of control, as I already mentioned in a previous slide. Armature. So what's your good name, sir?
Solke. Dr. Solke.
Yeah, sir. So there are two control we employ. One is armature voltage control, another is the field weakening control. Okay, so when armature voltage of the motor, DC motor is reduced, the armature current and hence the decreases, and thereby decreasing the motor speed, right? And this is coming from this relation. You see, this is the expression of this relation of a torque and the speed for the given parameter of a motor, right? So you have armature voltage here, and this is your this flux you have here. So by changing this armature voltage, the torque is reduced, and hence the speed is reduced. And in contrast, when the armature voltage is increased, the motor torque increases, and thereby increasing the motor speed. Okay, so to increase the speed of a motor, you need to increase the armature voltage, right? And under this, you see, this is the characteristic. Okay, so first you look at this characteristic. So these are the blue lines you have, solid lines you have, and this is the natural characteristic at a rated voltage. You can also see in the many literature you find that speed on the y-axis and the torque on the x-axis. Okay, so those who are familiar with those type of characteristics, they will find it you just have to look it by just turning it 90 degree, right? So you say this is a natural characteristic or a base characteristic we have with a rated voltage. Now if you have to change this characteristic, you have a parallel line, right? So by reducing this VA with a constant field, if you don't change the flux, right, your flux is constant, all other parameters are same, then the torque speed relation depends upon this VA, and you will find these parallel lines with the same slope. Okay, so this is the VA1 which is less than VA, this is VA2 which is less than VA1, and this is VA3, say suppose, which is less than VA2, right? So you will get this different this torque speed relation with a variation in armature voltage, right? So I hope this is clear, right? You will have a different this torque speed characteristic. So at a no load, you see, when torque is 0, these are the speed at a no load, and then with the increase in the torque, the speed will reduce. Okay, so these are the characteristic for the given voltage. If you have to maintain the speed, you need to increase the voltage, right? So it will follow this path, right? With the increase in a torque, you have a slight this reduction in a speed, and if you have to maintain that speed constant, you need to regulate this armature voltage. Okay, now another part, now once you reach to this point, that is VA, after that you can't increase this VA further, right? So here the motor can operate for any torque speed characteristic below the natural characteristic. Also the slope of this characteristic does not change with the speed, and since the maximum allowable armature current remains constant, this armature voltage control has the advantage of retaining the maximum torque capability at all the speed, and that is evident from that speed torque characteristic, right? But the armature voltage cannot be further increased beyond the rated value. Okay, so if the say rated voltage of the machine is say 220 volt DC, you cannot apply more than 220 volt for a continuous period, right? And this control, and hence this control is used only when the DC motor drive operates below its base speed. Okay, and then after this will come in a picture, that is flux weakening. So further above this base speed, if you want to increase this one, the speed, then these are the dotted line which represent the change in the flux. Now after this, you keep your armature voltage constant, which is the rated voltage, and you decrease the flux. And with the decrease in a flux, you will get a different these speed torque relations, wherein your this speed is increased, right? So when the field voltage of the DC motor is weakened while the armature voltage is fixed, so the motor back EMF will decrease. If you, as I have not included all the expressions of the DC machine right now, because that is not the discussion of our topic, but you can refer the basic, these are very basic mathematical expressions which are, and it's very easy to even understand the operation of a DC motor mathematically as well. You can also develop a simple mathematical model and do the simulation of that even in a MATLAB. I have that model, I will show you that in that simulation as well, right? So you can even write the basic equations, and then you can even develop the basic model. Okay, so the armature current will increase by an amount much larger than the decrease in the field, and thus the additional motor torque causes the motor speed to increase. Okay, so under this flux weakening control, the torque speed characteristic of the separately excited motor, which are shown with the dotted lines here. Okay, so above the base speed, you can keep your armature voltage constant and decrease the flux, and here the speed will then change inversely with this flux. Okay. And since you have that the characteristic, the slope of this character is no longer kept constant. Okay, it is affected by the flux, and you have that phi squared term as well here, right? Okay, so I hope that is clear to everyone, right? So so in order to achieve this wide range of a speed control, the armature control and this flux weakening control should be independent, and which can only be applied to the separately excited DC motor. No doubt, if you have that this shunt motor or a series motor, wherein this the field winding is either connected in a shunt with armature, or it is connected in series with armature, you have do not have an independent control of this armature voltage and the field, right? So below the base speed, as I already mentioned, the armature voltage is varied, whereas the flux is kept constant at a rated value, and so the field voltage which is applied to the motor will be the fixed. Okay, and since the maximum allowable armature current is constant, the torque capability under the armature voltage control can be kept constant. So the so-called the constant torque region. Okay, and above the base speed, we use this is a flux weakening control, and this is also known as a constant power region. Okay, so in terms of the capability, if you see the operating capability of this DC motor, then you have this the characteristic. Okay, so up to this point, you see you keep your torque constant. Okay, by changing this armature voltage, you can vary the speed, the current will also vary, and at this point your armature voltage is constant. Okay, so here the flux is constant in this region, and here the voltage is constant. Okay, and by changing the flux, you can then increase the speed, but the torque will fall and the power is constant. Okay, because that the voltage which is applied will be the constant, right? It is at this instant it is operated at a rated power, right? And then after you keep that power constant. Okay, so there is an effect on the torque when you further increase the speed by a field weakening or a flux weakening, right? Okay. Another aspect of these machines are the braking. Okay, so I will not go into much detail of this one, but this is also important. Okay, regenerative braking. Now, whenever you are using these machines in a EV, then you may be operating either that machine in a 1 quadrant or a 2 quadrant or even in a 4 quadrant. Okay, so I'll quickly explain those configurations as well when we use it. Okay, so so your motor may be operating either in a forward direction or in a reverse direction. And in a forward direction, when you apply a brake, then brake can be applied. There are various these methods which are applicable for applying the brake. Amongst them are the regenerative braking, and this is the most common braking which is used in the machine. Then we also have a rheostatic braking or a plugging. Okay, the advantage of regenerative braking is that you are operating your motor as a generator, and whatever kinetic energy which is stored will be transferred back to the source. Okay, so you have a the increase in the efficiency. Okay, so and generally this concept is widely used even in these locomotives as well, regenerative braking. Okay, so those who are familiar with the drives and the operation of this drive, this regenerative braking is widely used in this electric drive, right? And if we talk about a DC motor which is fed from the fixed DC voltage source, the regenerative braking can be performed only for a speed above the rated speed. Okay, where you are operating your this machine as a generator. Okay, but generally these machines are supplied with a DC chopper control. You have a DC-DC converter, so the input voltage of the machine can also be controlled, and hence it is possible to obtain regenerative braking down to almost the 0 speed. Okay, see to feed the power back. Now see, when we talk about the power, then you have a two parameter. One is a voltage and another is a current, right? So when both this voltage and current are positive, power will be transferred from battery to the motor. Okay, to reverse the polarity of a power, you need to either reverse voltage or a current. Okay, so if you reverse a current, then your battery will take the power from the generator, or even if you reverse the voltage, your battery will take the power from the motor. If you reverse both, then your machine is operating as a motor in a reverse direction. Okay, so to apply this regenerative braking, we need to control that voltage, right? So here with the DC-DC chopper, it's very straightforward to do that, and I will also show you that. Okay, so based on the 2-quadrant chopper which are used for the DC machine, the armature terminal voltage can be controlled with the use of a duty cycle, and your your source voltage will be less than the back EMF, so the armature current becomes negative. Okay, so when armature current is negative, it's in a reverse direction. Then the voltage at the terminal of the battery is positive, and the current is negative, and hence the power is negative. Okay, and it is also creating a negative for a torque for the regenerator. I will show you all the quadrant. I request all the participants to please turn off your mic if it is on. Some disturbances are coming, so please check your mic. If it is on, please turn it off. Okay, thank you. Now, when we talk about these converters, then the earliest system configuration of a motor drive for the electric propulsion consists of the mass of a resistors which are connected in series or a parallel with a DC motor. Okay, even as I was a judge in one of the event, and at that time some PG student came with one EV model. Okay, so the EV model means there was a simple robot which was driven by a battery, and they were using these mass resistors to control the speed. Okay, they were changing. Hello. Hello. Some
Yes, sir.
disturbances are coming. Yeah. Hello. Is
Yes,
this
sir.
clear? Am I
Now it's
audible?
audible.
Okay.
Yes, sir, you are audible.
Okay. Then that's fine. Okay. So earlier the people were using these resistors to control the speed of a motor. Okay. Obviously, when you by having a voltage drop across the resistor, you can control the voltage, input voltage to the motor. Okay, and then instead of a resistors, people also started using these transistors. They operate the transistor in a linear region, and it's again you have a voltage drop. Okay, but if you see, this is one simple voltage converter. So what you are doing is you have some input voltage here. This voltage may be say here it's a higher voltage, and on the output side you have a lower voltage. Okay, and you are regulating this voltage with the use of a converter. Okay, now this can be of any form. As I already mentioned, either you use the series parallel connections of a resistance, or you can go for this type of a transistors, and you operate this transistor in a linear region. Okay, now you can clearly see here, say the input voltage is 14 volt, the current which is supplied by the source is of a 10 ampere. Here also it's a 10 ampere. If we you see here, this is connected in series. Okay, the voltage on the output side is a 5 volt, and obviously there will be a voltage drop across this transistor, and that voltage drop is because you have to satisfy the Kirchhoff's law, right? And this has to be 9 volt. Now, if you compute this power, then the input power is of 140 watt. I request participant to please turn off your mic. Hello. Yeah. And the power on the output side is of a 50 watt. So you see the difference in the power. So you have a higher losses, 90 watts. So this type of configurations are not preferred. Okay. This is also, you can call it as a linear voltage regulators, wherein you operate this transistor, you give the command to the transistors, and you operate it in a linear region. Okay. So now we use this switch voltage converter with the use of these power electronics devices. Okay, so as you know that with the rapid development in the field of power electronics, this type of a linear regulators are obsolete, and for the DC motor control, and the DC chopper control has been used extensively for the DC motor drive. Okay, because they have advantages such as a smaller size, lighter weight, higher efficiency, and a better controllability, right? So basic configuration, if we talk, those who are familiar with these converters, those who are from the electrical background, and specifically the power electronics background, they may be knowing about all these type of converters. Okay, so mainly we have three types of basic configurations, which are known as a step down regulator, step up regulator, or a step down up regulator. That is also known as a buck boost regulator. Okay, so buck converter, boost converter, or a buck boost converter. These are the three common or a basic configuration for the converter. And once those who are just want to know about the concept, if they understand the basic principle of this converter, they can then easily understand the operation of any type of a converter, because most of the converters are designed based on this configuration. Okay, and these DC-DC converters, the term this DC-DC converter, or you are familiar with this SMPS or a switching regulator or a switching converter, or even chopper, they all refer to the same thing. Okay, and these operate by controlling the these power electronics devices. We use either say MOSFETs or IGBT. MOSFETs are generally used for the low to medium power applications, and in high power applications generally these IGBT switches are used. They act as a switch. Okay, they are the power electronic switches which can handle a higher power. Okay, and the switch interrupts the flow of a current to an energy storage component, and we use these capacitors and the inductor to store the energy, and then that energy will be transferred to the load. Okay, so the basic configuration, if you see, in comparison with that of the linear regulator, with the use of some sort of pulse width modulation. Okay, so what ultimately we are doing is we are turning this switch on and off at a say high speed. Okay, I will show you that how to do that and how we are controlling the output voltage. So in comparison with that of the linear regulator, here if you see the voltage is same, 14 volt, the output voltage is same, that is 5 volt. The input current, if you see here, it's a 3.76 ampere, whereas the power is 52.6 watt, and the output power requirement is same, that is of a 50 watt. So for the 50 watt output power requirement, the input power drawn by the combined converter and load will be around 52.6 watt. This is one simple example. Okay, so the efficiency of this will be around 95%. The losses in the converter may be of around say 2.6 watt or so, right? So this is the main advantage. That's why we don't go for those the resistor based or a linear regulator. Now when we talk about these switching voltage converters, or they are, you can also call it as a DC-DC converters or a chopper, okay, whatever you call it, they all are same. Basically, as I already mentioned, three configurations: the buck converter, which converts power from high voltage source to the lower voltage; the boost converter, which converts power from low voltage source to the higher voltage. So this is a configuration of a buck converter. The only thing is we are connecting these devices in a different fashion. Okay, so you have an inductor, you may also have a capacitor on the output side. These are the simple basic configuration to understand the principle of this converter, right? And these are the power electronic switches. Q here are the power electronic switches which are used. Okay, so in this configuration, the input voltage is higher compared to that of a output voltage, and that's why this is known as a buck converter or a step down converter. The power will be transferred from this HV side to the LV side. Okay, so if you are using this type of a converter for the DC motor, you can regulate the voltage from say the input voltage up to say the rated voltage of the motor. Okay, this is the another configuration which is known as a boost converter, which converts the power from low voltage source to the higher voltage source. Okay, so here in case of this boost converter, the output voltage is higher than the input voltage, and that's why this is also known as a step up converter. This is known as a step down converter, which will reduce the voltage and this will increase the voltage. Okay, so you have a controllability. The input voltage, sorry, output voltage will be higher than that of a input voltage. Another and third configuration is a combination of these two, which is known as a buck boost converter. So which converts the power from either input voltage source to an output voltage and can step down or step up the voltage. Okay, so the voltage level can be increased or it can be decreased, and that is controlled with the use of a duty cycle. Duty cycle means how or for how much time in a given switching frequency or a given period you turn on this switch, right? So based on by controlling this duty cycle of this converter, these switches, you can have a control over the output voltage. Okay. This is a basic operating principle. I have one small video. Okay, just a second. I'll just play. I see many times I show this video to my student as well. Can you see this? I don't know whether the audio will be. It's a 13-minute video, but I will play it only for 2-3 minutes, just to give an idea of how this the converter work. And it's very because I like it, and that's why I'm showing this to you.
Suppose we want to increase the voltage of our only battery.
Can you hear the audio?
Yes, sir. Yes, sir.
We have an inductor,
Sir, yes.
a
Yes, sir.
transistor,
Yes, sir.
a diode, and a capacitor. We also have a device to which we have to deliver power by a light bulb. The connection to the gate of the transistor is not shown, but this is a voltage that we control. Suppose we control this gate voltage in a way such that the transistor behaves like a switch, which we can turn on or off. If we close the switch, we will cause a DC voltage to appear across the inductor. The current through the inductor will keep increasing so long as the switch is closed. The current through an inductor cannot change instantaneously. Therefore, the moment we open the switch, the inductor will create a force causing the current to continue flowing. Suppose we keep turning the switch on and off. By continuously turning the switch on and off, we have created a DC output voltage at the light bulb that is higher than the voltage of the battery. We call this a boost converter.
So this is the configuration of a boost converter, right? So wherein the output voltage is higher than that of a input voltage. So what ultimately we are doing is we have connected this switch and the diode in such a way that, and the inductor obviously, when the switch is closed, at that time the energy from the battery will be stored in the inductor, and then after, when you open the switch, this diode will be in a forward bias condition, and whatever energy is stored in the inductor, that will be transferred here to the capacitor and the load, right? So this voltage, by properly applying the duty cycle or the switching signal to the switches, you can keep this voltage which is higher than that of a input voltage, and hence this is known as a boost converter. Okay, I'll not play the complete video.
We can control the value of the DC output voltage at the light bulb by controlling the percentage of time that this switch is on.
Now this is a configuration of this buck converter. Okay,
The diode will give the current a different path to flow through. We call this circuit a buck converter. We can control the value of the DC output voltage at the light bulb by controlling the percentage of time that this switch is on. This allows us to create any DC voltage at the light bulb that is lower than the voltage of the battery. Assuming that we had ideal components, this circuit would be 100% efficient. This is because ideal capacitors, ideal inductors, and ideal switches do not dissipate any energy as heat. We're thinking of the transistor as an ideal switch.
So I think the concept of this buck or a buck boost converter, or in general the DC-DC converter, is clear, right? So here you see this is the operating principle. Okay, so what ultimately we are doing is this is a simple a buck converter or a step down converter. Okay, so by controlling the operation of this switch, you control the output voltage. So what we are doing is this is our total time period, or we call it as a switching frequency of a converter, and we do not continuously supply the power to the load, but we supply the power based on the output voltage requirement. Okay, so we keep our switch on for some time. So this is the period for which we keep this switch on. So the energy will be transferred from source to the load, right? And then after we turn off the switch, the source is disconnected from the load. So the average output voltage will be less than that of a input voltage, right? So if you take even the average of this, then it will be less than that of a this input voltage. The ripple in the current depends upon the size of this inductor. You also have the capacitor which is connected across the load, which will keep the voltage across the load constant. Okay, so the proper selection of this inductor and capacitor is very much important. Right now I will not go into the detailed selection of those inductor and the capacitor, but if you refer any good book on a power electronics like Rashid or Bhimra or the Ned Mohan, you will find a very nice explanation about the selections of all these components for the DC-DC converter. Even you can refer these application notes from these of many companies like say Texas Instrument and all this. You will find a complete design this selection criteria for all the component for the DC-DC converter, right? But here in this type of a configuration, the output voltage will be less than that of a input voltage, and if you mathematically see, I will not go into all the detail, but if you want to just relate this output voltage with the input voltage, then this is how you can relate it, and this is basically done from those waveforms. Okay, so the output voltage V0 will be a Vs from the period 0 to t on. Okay, so when the switch is on, you can see here, when the switch is on, at that time only the input voltage is applied to the load, and when the switch is off, this load is connected through a diode. Okay, so whatever energy that you have, your inductor current will remain continue through this diode. Okay. And from this expression, if you just do the integration and find out the relation, then you have one parameter which is coming in a picture, that is known as this delta or a D, whatever you call it. Okay, in a different book or a literature, they give a different notation to this one, but this is known as a duty cycle or a duty ratio. Okay, so delta is nothing but a duty ratio. So if the duty ratio is 0, the switch is always off. the output voltage will be 0. If duty ratio is 1, switch is always connected to the and your voltage is continuously applied. Okay, so by varying this duty ratio or a duty cycle in the range of 0 to 1, you can vary this output voltage from 0 to Vs, right? And here this is known as a chopping frequency or a switching frequency, right? Now to control this or to generate this duty cycle, there are various ways to do it, right? One method and which is widely used is known as a time ratio control. And again, in a time ratio control, either you can keep your frequency constant or you can vary the frequency. So that there are two methods which are used. Another is a current limit control. This is used only when you have to keep your current within a limit, and it's not widely used, but mainly this first method is widely used, where we keep our frequency constant and we change only the on period. Okay, so here in this control, you see these are the different these waveforms we have for a different duty ratio. Okay, so here T1 is 1 by 2T, that is delta is 50%. Here it's a 75% and here it's a 25%. Okay, so your output voltage in this case is 50% to the input voltage 0.5 times Vs. Here this is 0.75 times Vs, and in a third case the output voltage V0 is 0.25 times the input voltage. Okay, and this T1 period is varied by keeping the total time or the switching frequency constant. Okay, so this T is fixed. You are only changing the on period. Another another option to change the duty cycle is you keep this on period fixed and you change this frequency, right? So that is another way to do that variable frequency system, wherein the T on period is kept constant but the T is varied. So if you vary this T, then also delta will be varied. Okay, so because they are dependent, right? So total time, so here you see in this case the total time period is this much. Okay, if you increase this total time period by keeping this on period fixed, then the duty cycle, which is the percentage on period for a given chopping time or a frequency, will reduce. Here it will be 66%. In a first case it is 75%, right? But obviously if you do this, this is another way wherein you keep your off period fixed and vary this time period. Okay, it's the same thing. It's a variable frequency system. So in a variable frequency, when you are changing this time period, either you keep your on period fixed or you keep your off period fixed. Okay, so if you keep on period fixed and vary this, then also your duty cycle will vary. Or if you keep your off period fixed and vary this time period, then also your duty cycle will change. Here in this case it's 50%, and here obviously here in this case it will increase. Okay, it becomes 66% because by increasing this time period, this on time is increased, right? Okay, but the problem is because the chopping frequency is varied or a wide range, the frequency modulation control, the filter, the design of this filter component for a wide frequency variation will be difficult. If you keep your switching frequency constant, then the harmonics which are produced or the variation in the voltage and current is known to you, right? So it's easier to design that the filter component. Another is whenever you are operating this converter with a larger T off period, if your off period is very large, there are chances that you go into a discontinuous conduction mode. Okay, mainly in a DC-DC converter, you have one is a continuous conduction mode, another mode of operation is known as a discontinuous conduction mode, and generally in a machine this discontinuous conduction mode is not desired. Discontinuous conduction means this current will become zero. Okay, load current should not become zero. So here you are increasing the current when the source is connected, when the switch is on, the source is connected to the load, and the inductor current will rise from I minimum to I maximum. So this is a peak to peak the ripple current you have, and based on this the requirement of your load, you design your filter either to reduce this peak to peak ripple, or there are other ways to do that as well. Okay, so here when you turn off the switch, your current will reduce and it goes up to this I minimum. Right. Now if you keep this switch off for a longer period, then whatever energy is stored in the inductor, that will be completely dissipated. And if it is completely dissipated, it will touch to this x-axis, that is zero line. Okay. So when all the energy stored in the load is dissipated, there is no current. It will reach to 0. So this mode of operation is known as a discontinuous protection mode. Right. So you need to consider all these aspects while designing the component for the converter, right? And last, the third one is the more possibility of interference with the signals and the telephone lines, because in a frequency modulation you have a wide variation of frequency. Okay, so that also needs to be taken care of, right? So generally there is a constant frequency system, or which we also call it as a PWM method, that is preferred. Okay. Another is a current limit control, wherein you just keep your current within a limit between these two limit, and based on that you turn off the switch. Okay, but this is also not widely used. Okay. Now when you have to generate the duty cycle for the converter, DC-DC converter, then for the generation of a duty cycle or on period, generally what we do is we have a reference signal. Like say what you do is you have a DC motor, you want to run that motor at a specific speed. Okay, you take the feedback of a speed, you feed it to the controller, and then controller will find out the voltage. You have a reference voltage, and then controller will, based on that reference voltage, controller has to find out the duty cycle, right? So that duty cycle is being generated once the reference voltage is there. The duty cycle is generated by comparison of that reference voltage with this type of a sawtooth carrier signal. Okay, so by comparison of this signal, you can generate these pulses directly. Okay, so if this reference voltage is increased, the on period will increase. The reference voltage will reduce. If you reduce this reference voltage, the on period will reduce. Okay, and by changing this, you vary your voltage from 0 to the maximum voltage, right? So these are the gate signals which are generated for your power electronics device, semiconductor device. Okay, so it will remain on based on your required input voltage, right? I hope this is clear. Okay, I'll show you one simple model in open loop as well as in a closed loop also I will show you. See, those who are doing the simulations, they can just a second. No?
Sir, there is a query of FDP 016 candidate. Please resolve
Yes.
that. FDP 016.
Hello.
Participant rule 16 number. You can ask question.
Hello.
Yes, go ahead.
Hello.
Yes.
Hello. Sir, actually, which type of converter is mostly used in EV? Boost, buck, or buck boost?
See, in a EV, I will show you that as well. You have to go for the configurations which will provide both this motoring as well as the regenerative action. Okay, so in a EV, I have that one of the slide where these converters are mentioned. Okay, so when you are using a DC machine, then hello, right?
Hello,
So
sir.
yeah. So what generally we have to do is we have to provide this the motoring action as well as the braking action. Okay, regenerative braking. So you need to go for a two quadrant kind of this configuration, or a full bridge type of a configuration, wherein you can achieve both these mode of operation. Okay, or many times in some of the EVs in one of the paper recently I've seen, where these 4 quadrant operations are being performed. Okay, that means when you are operating your machine in a motoring mode, you operate it in a first quadrant, then you have a second quadrant operation as well, that is known as a reverse, this one, braking. Okay, it's a generating action that you have. In a reverse direction, you operate your machine in a motoring mode, or in a reverse direction you operate in a this one, the generating mode. Okay, so I will quickly go through those configurations as well. Like you must have studied about this class A, class B, class C, class D, and all these choppers. Okay, single quadrant chopper, 2 quadrant chopper, or a 4 quadrant chopper, right? So these bridge inverters or a 4 quadrant choppers are widely used in many of the EV applications. Hello.
Hello, thank you, sir.
Okay, okay. Because only with a buck action, you can only control the speed up to that rated speed, and you only have a motoring action. Okay, so you need to
And
have
during regenerative braking, I think boost converter is required.
yeah, for the regenerative braking you need to go for a boost converter. Okay, so by combination of that buck and a boost, you can have a action of that motoring as well as the braking. Okay, and that way that is generally known as a 2 quadrant chopper, right?
Thank you, sir.
Yeah,
Yes.
yeah. Okay, okay. So you
Boost
see
converter
here.
is also used in the solar applications.
Hello.
Sir, even the boost converter is also used in solar applications.
Yes.
We
In the solar
require the DC voltage to be boosted.
boost. Yes. Yeah, you are right. It is also used there in this one solar applications. Okay. So see, there are many applications of that. You can even see in that. I'll show you that picture. I forgot the name of that machine which is used there. I think it was lunar. I forgot. If I recall that, I'll tell you that. Okay, I think it was a GMC conceptor. Okay, the machine or the EV which is known as this electrical G1. Okay, so they in that they adopted I think that separately excited DC motor for this the electric propulsion, and they were using that the bridge configurations in a 4 quadrant operation, right? So again, Nelco motor was used. Nelco, exactly I forgot the name. It was around the rated power was very high. It was around 45 kilowatt or so, with the torque of I think more than 300 Newton meter. Okay, and the transmission in that was the fixed gear. Again, see. It also depends upon whether see the type of motor, as I already mentioned, depends upon whether you are going for a fixed gearing or you have that other mechanisms. Okay, and forward and reverse actions will be achieved by changing the direction of or by changing the voltage with the use of a converter. Okay, so that is also possible, because in earlier EV, if you see, there are certain examples I have seen where the reverse action was achieved with the use of a gear mechanism. Okay, but that is not popular, because you have a bulky gears which are used in those mechanisms, and the cost is also higher. But with the use of an electric motor with a 4 quadrant operation, you can achieve all these torque speed characteristic in all the 4 quadrant, right? So and that's why this 4 quadrant operation of this converter is more popular for the EV applications. Okay. Okay, so now you see those who are working or doing some simulations. See, those who are working on a EV, before you just start implementing anything, or specifically those who are doing research, they can start with the basic concept, understanding of a DC machine with a converter. Okay, so you see this is a simple open loop control of a separately excited DC motor. Okay, so here we are using a DC motor in a MATLAB. Can you see this diagram? It's a motor, and this is a buck converter, step down converter that we are using. We have a MOSFET. Okay, now as I already mentioned, when you have to generate this type of a duty cycle or a signals for the switch. Those signals can be generated with the comparison of your this repetitive sequence signal. Okay, these are the sawtooth waveform that you have with a fixed value. This is your duty cycle. Now in an open loop control, you can directly specify this duty cycle, whereas in case of a closed loop control, this duty cycle will be generated by your controller. Okay, and these two signals, now what I'm doing is I have just implemented these two here in this block. I'm comparing this sawtooth waveform with a fixed input voltage. I'm using a step signal here so that I can also give the step change in the duty cycle. So initial value of my duty cycle is 0.5, and then I'm increasing this duty cycle to 0.8 at say 1 second. Okay, so with the increase in the duty cycle, as you know that in a buck converter, the output voltage of the converter will increase, and hence the armature voltage of this machine will increase, and you can see the change in the speed. Okay, and by keeping this duty cycle constant, if you give a step change in the torque, so initially the load torque is at 10 Newton meter, and it's a 2 second, I will change that torque to 15 Newton meter. Okay, so by keeping this voltage, if I increase the load on the motor, then the speed will reduce. Okay, so to adjust that speed, you need to increase the voltage, and that you can do in a closed loop control. Right now, this is a simple open loop control wherein you are generating the gating signal for this power this MOSFET by comparison of a sawtooth waveform with a fixed value, right? Okay, and the field is constant, and this motor is just a second. So this is a 5 HP 240 volt 1750 RPM, and the field voltage is of a 300 volt. Okay, so this is a simple open loop control of a chopper fed separately excited DC motor. So if I run it, just a second, I'll show you this output voltage. When the MATLAB is run with this MS team, at that time I'm facing this problem. And see, another thing is many times I just tell my student initially not to use any of the model which are given by any of the software. Okay, this is MATLAB we are using right now. You can also use other software like say PSCAD or so, right? So instead of using the ready-made models of all the components which are given in a MATLAB, you should try with the mathematical equations so that you can simplify your this simulation system. Okay, because see these machines which are being implemented here are being implemented with all the detailed equations of a machine. Okay, so obviously when you are doing the simulations with a built-in models which are given in any of the software, they take much time. Okay, instead of that, initially if your requirement is just to test your controller with basic parameter, you can develop your own mathematical model for the machine and use it so that the simulation time can be reduced, right? So here if you see the outputs, these are the three the signals we have. The first one is the speed, second is the armature current, and third one is the torque. So initially I kept some duty cycle of 0.5. So for that 0.5 duty cycle, this is the speed I have. The torque, I'm having a 10 Newton meter. So accordingly, you have that current as well, which is of a 10 ampere. And at t is equal to 1 second, I'm increasing the duty cycle from what is that? What was that duty cycle? Let's check it. Yeah, 0.5 to 0.8. So if you increase the duty cycle, then your speed will the armature voltage will increase with the fixed field voltage, and hence the speed will increase. You see, the speed will increase further, and it is around say 1500 RPM. Okay, and by keeping that armature voltage constant, if you give a step change in the load torque, then at this instant, if you see at t is equal to 2 seconds, here also in the simulation module you can see that I'm changing the load torque from initial value of 10 to 15 Newton meter at t is equal to 2 seconds, then the speed will reduce for the the same voltage, because I'm not doing anything with the armature voltage, right?
Excuse me.
Yeah,
So, small question.
yeah.
So you
Go
are
ahead.
doing it in simulation by varying the values in the simulation model.
Yes.
How do you do physically on the ground when you are having this motor, DC motor and you converter and the components are there? How do you change those cycles, duty cycle and the? How do that?
Yeah, good. Here we are doing it in a simulation, and we give the fixed DC voltage. Here this is open loop control, so our input is fixed, and that is in terms of a duty cycle. Okay, so it will run at a specific speed only. Okay, as I already mentioned earlier, if you see that diagram, configuration of a EV earlier, right? This is the main this EV configuration. So practically, if you see, then those signals are given with the use of this accelerator or a brake. Okay, these are the input signals which are given by the human being to control this motor. Okay, so ultimately the speed of the motor is being controlled with the use of these signals. You may also have other inputs from the system as well. Now this signal will then be given to the controller, and this vehicle controller will generate the required signal. Like say if you have a DC-DC converter, then the duty cycle will be generated by this controller, and duty cycle of say 0.5 or a 0.8 will be given to the converter. So the converter will operate in such a way that you will get the desired speed. Got it?
Yes.
Yeah. So now see, right now I have not included this closed loop control. Okay. Now this you may be taking the feedback of a speed because what is done here is if the load is increased, then it may happen that your speed will reduce, and that is what we have observed here in this case. When I increase the load, the speed is so you need to apply more acceleration. Okay, to increase the armature voltage. Okay. So you can also have a closed loop control. So this another diagram, you can further extend this. So what I have done is, this is a closed loop control. So in a closed loop control, what is generally done is you take a speed reference, feedback. You take a, see, there is a difference in open loop control and a closed. In case of a open loop control, you do not have any feedback system. Whereas in a closed loop control, you have a feedback system. So for the given input, if you want to keep your speed constant, then you take the feedback of a speed, and that feedback you apply at this comparator. Okay, so here is your reference speed. So irrespective of the load, the speed will remain constant because you are taking the speed as a feedback. Okay, so this diagram is saying, you see here, you have a comparator, you have a repetitive sequence here, and the another input which is given to this comparator is this one from the controller. So now you have a PID controller, proportional integral derivative controller. Okay, and this controller will generate the reference signal which is being compared with this repetitive sequence, and finally the duty cycle will be generated. Okay, so I'm taking the feedback, and here see I just to give various signals, I have prepared a lookup table with a clock so that you can change the speed reference. Okay, so these are the various speeds. I'm changing the speed manually. Okay, this speed you are practically you are changing with the use of that accelerator. Okay, so you give the signal to the accelerator based on the required speed. If you want to increase the speed, you apply more acceleration. If you want to reduce the speed, you apply less acceleration. Okay, so this is what we are doing at a different time period here, right? So you can see the variation here in a single graph, right? And this is the feedback that I'm taking. In a motor block, you also have a measurement port from where you can do the measurement of various parameters, and you can use it either to give the feedback or just to monitor it. Okay, and the load torque initially is 0, so motor is operated at no load, and then I'm changing it to 10 Newton meter at say around 0.75 second. Okay, I'll show you the effect. Okay, we'll see the difference in an open loop and a closed loop. Okay, this is, So here, if I just open this, there are various the signals you have. The first one is the speed, second one is the armature current, and third one is this torque. You find some bumps here, and that depends upon how you tune your PI controller. Okay, ultimately that controller is generating the reference signal. Okay, so in a PI controller you need to specify those values of a proportional and an integral gain. Okay, those who are familiar with a control system, they may be knowing about these control gains. Okay, mathematically you can find out these values, or by trial and error. Generally, in most of the cases, we do it by trial and error. Okay, there are other standard methods like Ziegler-Nicholas method and other many methods reported in the literature. Even MATLAB also, you have a functionality to tune this PI controller, so you can find out these proper values of this constant. Okay, so how effectively you tune this controller, based on that you will get the dynamic response. Okay, so here you see up to this point my speed is increased from 0 to 100 RPM. Okay, and from this point to this point speed is constant. Now at this instant the load torque is 0, and at t is equal to 0.75 I am giving a step change in the load torque. When I give the step change in the load torque, if I am using a closed loop control and if I am keeping my speed constant, my controller should act in such a way or generate a duty cycle in such a way that it will keep my speed constant, and that is what is done by the controller. You see here the speed remains constant at 1000 RPM even if you give a step change in the load. Okay, and that is not happening here in open loop control. In open loop control, when I've increased this load torque, when I give the step change to the load torque from 10 Newton meter to 15 Newton meter, at that time the speed will reduce, because I'm not doing anything with the this one, the duty cycle, or practically you are not doing anything with the acceleration, right? So if you are climbing during the hill climbing, you need to apply, your load is increased, okay, you need to apply more acceleration to the motor. Okay, because there is a change in the load. So when there is a change in the load, obviously speed will reduce. But in automatic control or in a closed loop control, you can keep your speed constant by having a feedback control, and that is being done at here. Okay, at this instant with a constant torque, I am changing the speed, right? If I give a step change in the speed, so at this point at t is equal to 1 second, as well as at t is equal to 1.5 second, I am changing the speed. Okay, here I am reducing the acceleration, so the speed of the vehicle will reduce, speed of the motor will reduce. At this instant, again I am increasing the acceleration, so the speed of the motor or the vehicle will increase. Okay, it goes up to say 1500 RPM, and at this instant again I am reducing the speed. Okay, and simultaneously the load torque is also changed, right? So in this way, I say this is one way. Okay, this is what I have done in this simulation. I have applied various changes in the speed as well as some changes in the torque. So based on the study that you are carrying out, you can just apply different signal to the system and see the performance of a system, right? Okay, so that was one, this is a closed loop control of DC, that buck converter that we have. Okay, so see, once you understand the operation of any of these converter, then you can then apply those concepts to other converter configurations as well. And as one of the faculty asked about the different types of configurations, so as I already mentioned, based on the mode of operation, you will have a different DC-DC converter or a chopper configuration. Okay, so generally we have mainly 4 types of these operations. Okay, so here you can see this we call it as a first quadrant operation. This is a second quadrant operation, third quadrant operation, or a fourth quadrant operation. Okay, in a first quadrant, the speed is positive and torque is also positive. So the power is supplied by the battery to the motor. Okay, so you are taking the power from the battery. This is known as a forward motoring. Okay. The second, when you reverse the speed, if the direction of this motor is reversed and the torque is positive, this is known as the reverse generating. This is a generating action. So the power will be supplied back to the source. Okay, your machine will act as a generator and it will feed the power back to the source. Your battery will charge. If the speed and torque both are negative, that means your voltage and current both are negative. Okay, in that case, it is known as a reverse motoring. Okay, so when you are say parking your vehicle and you are moving it in a reverse direction, at that time you have to operate your vehicle in a third quadrant. So speed and torque both will be negative, or the voltage and current both will be negative. So the power will be again supplied by the battery to the motor, but this is known as a reverse motoring. And when you are moving at a fast speed in a reverse direction and apply a brake, at that time the kinetic energy will be transferred back to the source if you are operating it in a fourth quadrant, wherein the speed may be positive and this is negative. Okay, actually this too will be done in a reverse motoring, and the first quadrant and fourth quadrant will be in a forward when your electric vehicle is running in a forward direction. Okay. So see again this table or this quadrant depends upon whether you take your speed on a x-axis or a torque on a x-axis. Okay, so in a literature you will find that torque speed characteristic with a speed on x-axis and torque on y-axis, or the torque on x-axis and the speed on a y-axis. Okay, so based on that you can find out the polarity. Okay, and see practically if you see, the machine is limited in developing this high torque. Okay, so when we talk about this speed torque characteristic of a motor, then you have two types of this operation. One we call it as a continuous operation, another is a transient operation. Right. So the transient operation is for a short duration. Right. So this machine is limited in developing high torque, as the required current can result in excessive winding heating. Okay, you cannot draw a more current for a long period, right? And the possible machine failure. So thus the four quadrant operation, four quadrant speed torque characteristic if you draw, then practically you have in each quadrant you will have a two operation. The one is known as a continuous operation, another is known as a transient operation. Okay, so this is again based on that what I would say that constant torque and constant power characteristic of a DC machine, which we discussed earlier, right? So you can keep your torque constant up to this period or up to rated voltage. Once you reach to the rated voltage, you cannot increase that voltage further, right? But you can do it for some time, that is known as a transient period. So your machine can be operated for a continuous operation in this region, and it can be operated in a transient region for a shorter duration of time. Okay, so here either you can increase the torque or you can increase the speed in a constant torque region or a constant power region. Okay, and it is applicable in for the region, all the four quadrant, right? So what's the time? Okay, see, I'll quickly go through this. Okay, I'll not go into the operation of all the converters, as one of the faculty already asked about that types of choppers which are used. Okay, so we have a first quadrant chopper or a second quadrant chopper or a two quadrant chopper or a four quadrant chopper. So when you have to operate your machine in all the four quadrant, so this class E or a four quadrant chopper configuration is preferred, right? And you can also relate this quadrant operation in terms of a voltage and current, similar to that of a speed and this one, the torque, right? Again, here either you can have this V0 on x-axis or I0 on a x-axis. Okay, so based on that, the polarity will change. Okay, so this is what I already explained. It's a first quadrant chopper. It's also known as a step down chopper. Okay, so the power will be transferred. It will operate only in a one quadrant, and by this operating this switch 1, you can control the output voltage. Okay, this is also known as a step down chopper. Okay, and your output voltage will always be less than that of this input voltage. This is a second quadrant chopper or a class B chopper. Again, this is only a single quadrant chopper, but it operates in a second quadrant, okay, wherein the current is negative. So when you have to go for a regenerative braking, at that time, either you have to change the polarity of a voltage or a current. Here you are changing the polarity of a current, and hence you can feed the power back from the motor to the source, and this configuration is same as that of a step-up chopper, okay. And by combining this step up and step down chopper, you can operate this configuration. This is a half bridge configuration, which is also known as a class C chopper or a two quadrant chopper type A, okay, because in a two quadrant you have two types of chopper. Either you operate in quadrant 1 and quadrant 2, or you operate your or you have a configuration which operate in quadrant 1 and quadrant 4, right? So here, by using these two switches, this is nothing but a combination of a step up and a step down chopper, okay. So you can operate, so if you are using this type of a configuration, you can operate your EV either in a motoring mode or in a generating mode, okay. That is known as a regenerative braking, okay. So you either get the power from the battery, or you supply power back to the battery during the braking operation, right? So the direction of current is reversed, polarity of the voltage will remain same. Another configuration of this two quadrant is type B, okay. So this is also known as a class D chopper. The configuration is slightly different, and hence here what you are doing is, again you are operating your machine in both the mode, that is a motoring mode as well as generating mode, but the generating mode is achieved by changing the polarity, okay. So you have arranged the switches in such a way that you can reverse the polarity of voltage which is applied to the motor, okay. So the direction of current will remain same. You see here, this is minus V0, so the direction of the voltage or the voltage polarity is reversed, so the power is reversed, okay. So this is known as a generating action, and this is a motoring action, okay. So it depends upon.
Excuse me, sir. Mukesh,
Yes,
sir.
yes.
Last 5 minutes, please.
Oh, okay.
Try.
So see, I will not go into all the configurations now because we do not have the much time. But mainly, see, if you see, I'll quickly just see. My objective is not to give in-depth knowledge about all the topic, but just to give a bird eye view of what type of converters can be used and how they are being controlled, okay. And many of these converters are tested in a EV, and some of the configurations are already used in this EV, okay. So this is a 4-quadrant operation wherein you can operate your machine in all the 4 quadrants, okay. See, the operation will be same as that of this class A and class B chopper. Only thing is you are combining both this chopper in both the direction, okay. So by combinations of those class A and class B chopper in a different configuration, you can operate your machine in all the 4 quadrant as well, okay. So I will not go into detail of this, but these are the different modes of operation. I will share this PPT with you so you can go through all these as well, okay. So this is first quadrant operation where this voltage and current both are positive. This is again a first quadrant operation. Here in a first quadrant you are controlling this switch S1 and S4, okay. So these two, and that is what is mentioned here, okay. So this by controlling this 1 and 4, so 1 is controlled, this switch number 4 is continuously turned on, right. So you control this switch 1, and by doing that you can regulate the voltage, armature voltage across the motor. This is a second quadrant operation, okay. Wherein the direction of current is reversed, the voltage polarity will remain same. So you are operating your machine in a this one, the regenerative braking mode, and you can operate this with the use of this switch. You see here the power is supplied back to the source. The current is negative, voltage is positive. So your machine is supplying the power to the source, and this is being done by controlling this switch S2, okay. Then we have a third quadrant operation. Similarly, in a third quadrant, both this voltage and current are negative. So your motor or the vehicle is operating in a reverse direction. So the power is supplied again to the machine, okay. And in a last or a 4 quadrant, fourth quadrant, it is reverse generating. Okay, so while moving the motor in a reverse direction, you can use this the regenerative braking action. Okay, so and in this way you can operate this machine in all the four quadrants. This is electrical equivalent diagram for all the four quadrant or a multi quadrant operation. Okay, so in this case you can see this is forward motoring where armature voltage is greater than the back EMF. This is known as a forward braking where armature this battery voltage is less than the back EMF. This is a reverse motoring. Okay, so the current is negative. You can see the polarity of voltage of a battery. So, yes.
Sorry to interrupt you, sir.
Yes. Yeah, go ahead.
In the third quadrant, both the speed and torque both are negative. So
Yes.
the motor is moving in the reverse direction. So during backing, backing of the vehicle, that means when we back the vehicle, then only this motion is required.
Yeah. Whenever you are operating in a reverse direction, okay, so you are parking.
Parking or okay, going backward direction.
Going backward direction. Okay, so whenever you are going in a backward direction, at that time only you have to operate it in a reverse motoring mode. Yeah, you are right. Okay. And see, if you see the literature, you will also find some gear mechanism. Okay, reverse gear mechanism is also implemented in some of the EVs, right? But as it is already reported that that is bulky, costly, and hence it is not preferred. Okay, because it's not economical, right? So you have this reverse gear. So if
this mode is much more preferable.
yeah, that's why, yeah, you are right. So that's why this is preferred. Okay, because if you do not have this mode available, then obviously to move your vehicle in a reverse direction, you need to have some sort of mechanical mechanism which will move your vehicle in a reverse direction. Got the point, madam?
Got the point.
Yeah. I'm not now going into much detail. As I already mentioned, okay, I'll just quickly, you can also see those who are doing some mathematical analysis or doing some simulations, instead of using those ready-made models which are given in the simulation software, you can also develop your mathematical model in this way. Okay, so this is one dynamic model of a DC motor. So this is much simpler compared to that of the model which is implemented in a MATLAB or a PSCAD. Okay, because they are the detailed model which are implemented. So if you are running your simulations for longer time, at that time it will take more time to do the simulations. Okay, so if I have to if I'm using a closed loop control system and I'm doing the simulations for 20 seconds or 30 seconds, it takes a lot of time. So you can simplify those models with the use of these mathematical equations. Okay, so here, okay, just a second. If I show you one simple such model which I've implemented, I don't know whether it's there or not. Yeah. Yeah. It's very simple, okay, and I generally suggest my students, okay, so whenever they start studying about a DC machines or a drives, at that time I tell them not to use that ready-made model which is given in a simulation software. Instead you go for, so that you will also understand the concept. Okay, so this is a simple, so this is a DC machine. I would say this is a DC machine that I am simulating. Okay, so it's a speed control of a separately excited DC motor using a dynamic model. Okay, so the same type of output you will get as of the built-in model which are given in the simulation software. No doubt this is a simplified model, but it can be used for the basic simulations. Okay, and you can run it very quickly. You see the time taken is also very less, and these are some of the waveforms which I got. Okay, I'm giving a step change in the speed or a torque. Okay, so speed I'm changing. So simultaneously by keeping the torque constant, the back EMF will change if I change the speed. The armature current will remain constant because the torque is constant, right? So in this way you can even implement this model. Okay. Now due to lack of time, because I have a lot of material, but it's not possible for me to complete everything. This is one isolated DC-DC converter. So this is a closed loop control. I already explained those model in the MATLAB. Okay, one of the model. Another the type of converters which are in some of the EVs which are implemented are the isolated converter. Okay, and they are used mainly for the safety purpose. Okay, and there are many configurations which are reported, but in one of the Ford, I think Ford have implemented one this isolated DC-DC converter. It's a forward converter which they, I don't know what's happening. Yeah, it's a change. So this is one the automobile, this one, the converter which is used in one of the Ford vehicle. Okay, so ultimately this see flyback converter is derived from that buck boost converter. Buck boost converters are the transformer relays converter, and these are based on the transformer. Okay, so this type of configurations can also be used. Okay, so I will not go into the detailed operations of this, but once you have understood the basic operations of these converters, you can easily derive other aspect on this. Okay, so I will upload this PPT. Another aspect, soft switching, as I already explained earlier, you can also go into this. Some applications have included, this is a lunar roving vehicle using a DC motor. Okay, so these are some of the details which are given related to this mission, which was of the Apollo lunar surface mission. Okay, so where in a vehicle they have used this DC motor. Okay, then another aspect is the induction motor drive. So due to lack of time, I'm not going into all these converter control and configurations, but you can refer this. Okay, various control methods like SPWM, third harmonic injections, or space vector modulations are used for the control of these inverters. Okay, so you can use it. And the last part is permanent magnet brushless DC motors. Which is another breed of motors which are nowadays very popular, and many people are working on this type of a motor. Okay, and these are the control aspect, and these are some of the vehicle, like say this is a Nissan Leaf, in which they have used this the permanent magnet synchronous motor. Okay, which can which is having a this power rating of 80 kilowatt. Okay. And another is this smart 420 electric drive. They have used this BLDC motor, okay, permanent magnet BLDC motor. Right. So these PM brushless motors are nowadays preferred technologies for EV, and many people are working in this area. And it is anticipated that both these members will equally share the market of this brushless motor drive, that is two-wheel as well as four-wheel. Okay. So you can refer these books as well on this. So now I could not go into much detail of other aspect due to limitation of time, but if you have any question you can ask, otherwise, yeah, sir, over to you.
Thank you very much for your nice speech. Now any question, any participant have any query?
Excuse
please
me,
ask.
Sir, I have one query, sir.
Yeah, go ahead.
Sir, my question is regarding this DC-DC converter, sir. Sir, we have this bidirectional DC-DC converter. So
Yes.
is it same as a chopper, or is there any difference? Can we call it as a chopper, bidirectional DC-DC converter, or is it anything?
Yeah, as a bidirectional, when you say you are just transferring the power from input 1 to input 2, or from input 2 to input 1, right? So in case of many of the chopper configuration, here you are transferring the power from either battery to the machine or machine to the battery. Okay, so in principle they will be same. Now see, again I'm saying that in many, some of the applications the configurations which are used may be different, but those topologies are derived basically from the three basic configuration, that is buck boost and a buck boost.
Okay, sir, thank you.